Hello and welcome to our presentation. In this work, we introduce a novel hybrid manipulator designed for minimally invasive surgery. The system integrates two soft pneumatic segments for safe, adaptive navigation, and a distal cable-driven section for precise tissue interaction. Soft robotic segments act as intrinsic mechanical force limiters, enabling the robot to passively conform to the colon wall and minimize the risk of injury. This compliant behavior is especially critical when the robot operates outside the visible endoscopic field. To overcome the challenge of maintaining both compactness and force output, we designed morphable chambers. These chambers modulate stiffness by varying their internal pressurization, allowing the actuator to remain flexible at rest, but increase rigidity and payload capacity as needed for clinical tasks. However, morphable chambers exhibit highly nonlinear, history-dependent behavior. The internal stiffness changes dynamically with pressurization, leading to significant hysteresis that complicates precise open-loop control. Another critical challenge is intersegmental crosstalk. When one segment is actuated, it can induce unintended movement in its neighbor due to mechanical coupling through the central lumen. This crosstalk introduces additional nonlinearity, further complicating open-loop control and accurate trajectory tracking. To address these challenges, we employ sequence-based machine learning models. Using LSTM and transformer architectures with augmented state inputs, our models capture both temporal dynamics and nonlinear interactions like hysteresis and crosstalk. This approach enables more robust and data-efficient inverse kinematics, even with limited training samples. In single-segment experiments, we observed that when using only the current state X as input, the model predicts nearly identical pressure sequences for both clockwise and counterclockwise circular trajectories, failing to distinguish the motion direction. By switching to the augmented input state U with a time window of m equal to 2, the model captures the underlying dynamics and produces pressure commands that more accurately follow the intended trajectory, reducing tracking errors and improving performance. For two-segment robots, we compare our proposed recursive segment-wise crosstalk compensation pipeline, or RSCC, against a conventional multi-segment LSTM baseline. Trajectory tracking results show that the RSCC pipeline achieves significantly lower positional errors in both proximal and distal segments compared to the conventional LSTM approach. The RSCC method maintains accuracy even with fewer training samples, enabling open-loop control for morphable chamber designs in teleoperated surgical applications. Here, we test robustness under payloads of 5, 10, and 20 grams. The RSCC pipeline continues to track the circular trajectory reliably, showing minimal error below 10 grams and only deviation at 20 grams. Thank you for your attention.